right, how do we multiply two vectors together? There's two ways to do it. We can multiply them together in order to get a scalar answer, and we can multiply them together in order to get another vector as an answer. Today, we're just going to cover multiplying them together to get a scalar. So that's why it's called the scalar product or the dot product, and it's called the dot product because of the symbol that we use. So why we're doing this today is because yesterday we talked about calculating the potential from an electric field. And we did that for a specific example for a point charge. But in general, we have to do this integral. We have to integrate the electric field the dot product of the electric field with the path that the charge is going to take when it changes, when it goes through a potential difference. So we need to understand what we're doing here when we take these two vectors, right? The electric field and this dr, this path element, are vectors. And then we multiply them together using the dot product. So I'm going to just look at two generic vectors, not necessarily the electric field and the displacement, but just two generic vectors, A, here's vector A, and here's vector B. And they have some angle between them. It's what we can call theta. The definition of a dot product, when we multiply these two together, A dot B, we multiply together their magnitudes. So the magnitude of A and the magnitude of B. And then we also multiply the cosine of the angle that's between them. So in this case, when we're doing these dot products, we have to remember that this angle isn't usually when we think of an angle associated with a vector, we think of the angle the vector makes with the positive x-axis. But in this case, this is just the angle between the two vectors A and B. All right, so visually, we can see what we're doing when we take the dot product. We're really multiplying just the components of the vectors that are parallel to each other. So if our vector A is like this, right, there's a component and vector B is like this, there's a component of A that's perpendicular to B, and there's a component of A that's parallel to B. This component of A that's parallel to B is just A cosine theta. So what we're really doing is multiplying these two lengths. Right, so the component of A that's perpendicular to B has a certain length, certain magnitude, and if we multiply that with the magnitude of B itself, we get the dot product. And A and B can be switched, so we could also look at it this way. If this is vector A again, and vector B was like this, we can also say that vector B has a component that's parallel to A, which looks like this, and a component that's perpendicular to A, which is like that. And this here is B cosine theta. So the other way to visualize multiplying these two together is by these two lengths. So, or these two. So it really doesn't matter if you multiply the magnitude of A cosine theta times B, or the magnitude of A times the magnitude of B cosine theta, right? You get the same thing either way. So it can help when you are multiplying vectors together using the dot product. It can help to visually understand what you're doing there. That's why I took the time to draw out these two diagrams. Are we okay so far? So there's a couple of shortcuts or a couple important things to know, such as when vectors are parallel or anti-parallel. So if we have two vectors like this, where A and B are both pointing in the same direction, what are we going to get as the dot product of these two vectors if they're parallel to each other? Or what I'm asking is, what would the angle be between vector A and vector B if they're pointing in the same direction?
Can you rephrase that question? I only understood like part of it.
Yeah, so I want to find out. I want to use this this formula here to figure out the dot product of A and B. In this case, I have two vectors that are parallel to each other. So what am I going to get for my dot product?
Absolute value of A times A times B.
Okay. Yeah. Right. The absolute value or the magnitude, since we're talking about vectors.
Yeah.
But it is the absolute value. Very simple. So we get A times B, and then what's the what about this part? The cosine.
Well, there is no angle. You can say cosine is 0, right?
Right. And we know the cosine of 0 degrees
Is 1.
is 1. So if the vectors are parallel, we just have to multiply their magnitudes together. Right? It's just A times B, the magnitude of A times the magnitude of B. All right. And that's important to know and useful to remember. What if we have vectors that are anti-parallel? So if A is like this and then B is like this. So
subtract.
We subtract? Well, we're multiplying them, right?
Divide A from B.
You can say one is negative and the other is not, right?
Well, let's just use this same formula again.
Oh yeah.
The only thing that's different, right, is the angle.
Oh yeah, it's opposite.
Yeah, so it's not a 0 degree angle between these two vectors, right? What's the angle between two vectors that point in opposite directions?
180.
180. Right? A and B are separated by 180 degrees now. So now I use the cosine of 180 degrees. Or
-1.
yeah, and the cosine of 180 is -1. So if the two vectors are anti-parallel, I just get negative of the two magnitudes multiplied together.
So you still multiply them?
Yep. Yeah, we're still right. This is an operate, right? We can learn probably 10 years ago at this point how to multiply numbers together, right? But then we've kind of expanded what kind of objects we can do math with, right? We can do math with more than just numbers. We can do them with something that's a little bit more complicated. That's called vectors. And we've already seen how we can add vectors together, but multiplying vectors together is a little bit more complicated. Right, and there's actually two ways to do it, and this is the first way to do it, the dot product. This is the way to multiply two vectors together and end up with a scalar as an answer. And the reason this is the way to do it, this isn't just made up, it's because it can be shown, and we're not going to go through and see everything. But if this is the definition that we take for the way to multiply two vectors together, then the multiplication kind of works exactly as we're going to expect it to. It's going to be commutative. It's going to be associative. If you have two vectors that are pointing in the same direction and you multiply them together, it's just like multiplying their two magnitudes together. So really what we're just doing is expanding what we can do math with beyond numbers into vectors, because that'll help us solve physics problems. So when we do multiply vectors that point in opposite directions, we get a negative number. We get their magnitude multiplied together, a negative number. And finally, the last special case we'll look at is what if they are perpendicular to each other? Maybe you can already tell what the answer is going to be. If I multiply two vectors together that are perpendicular, so this time A can say point upwards, and if B points to the right, A dot B, I'm still using this same formula here, magnitude of A, magnitude of B, and what's the angle and then the cosine that I get this time. Well, what's the angle between two vectors that are perpendicular to each other?
90 degrees.
90 degrees. Right, so this time I have the cosine of 90 degrees, which is
Pi over 2.
Is it?
Cosine of 90 degrees?
What's the cosine?
0.
Oh, yeah, 0. Whoops.
Right, 90 degrees is pi over
Yeah.
2 radians,
Yeah.
and the cosine of that is 0. So if we take the dot product, if we multiply two perpendicular vectors together, we get 0. And that's because there's no component of A to multiply by B, and there's no component of A that's parallel to B, right? And there's no component of B that's parallel to A. So we end up with 0. Okay, so this is the defining formula of a dot product, and this is the useful one to use if you know what the magnitude of the vectors are and you know what the angle between them is. But we can also, sometimes we know what the components of the vector are and not necessarily what the magnitudes and the angle are. And in that case, we want to see how to do this using unit vector notation. And I think I will go on to another sheet of paper instead of trying to cram it in that corner. And we're almost done. This is only going to take another 2 minutes, 3 minutes. So for unit vectors, if we have our vectors in unit vector notation, right, which means that we have our vector A written as some x component of A times I hat plus some number that's the y component of A times j hat, right? We already know what unit vectors are. Any vector, you can write any vector as its x component times I hat plus its y component times j hat. And then vector B, we have something the same, right? B is going to be the x component of B times I hat plus the y component of B times j hat. So we can just, now let's just use what we know about multiplication to multiply these two together, right? So if we want to do A dot B, we're just going to multiply these two things together. AX times I hat plus AY j hat multiplied with BX I hat plus BY j hat. And this is algebra that we can all do, right? So I have this first term, the terms on the left here. So I have AX times BX times I hat times I hat. And the I hats are really, this is a dot product, right? So the I hats are dotted together. And then I have this term, the AX I hat times the BY j hat. Whoops. So that's AX, sorry, that's AX times by times I hat times j hat. Since they're vectors, I dot the I hat and the j hats together. Then I have this term, the ay j hat and the bx I hat. Oops. So that's ay times bx. Sorry, it's these two. So that's ay times bx times j hat dot I hat. And then my last term is these two. So ay times by times j hat dot j hat. Okay. So this we can simplify down a lot. So first of all, I have a couple of terms here that have an I hat dotted with a j hat. Can we tell quickly what value that's going to be? I hat dot j hat. If you remember what I hat and j hat are.
Would it just be the vector?
Well, yeah, but okay. What vector?
Like
I
the
had
two of them combined?
two of them combined, two of them dotted together. Yeah. So if we remember what is I hat? What's the vector I hat?
X direction, or the x-axis.
It points along the x-axis, right? So let's draw I hat. It points along the x-axis, and what's its length?
Depending on how much force.
Not for I hat, right? I hat's got a certain length. Anything with a hat has a certain length.
1.
1, right? It's a unit vector. So I hat's got points in the x direction, and it's got length 1. What about j hat? How did we define j hat the other week? It's got a hat, so it's also length 1. What direction does j hat?
The y direction.
Yeah, in the y direction, right? J hat is the unit vector, or the vector that has a length of 1 that points along the y-axis, right? Along the positive y-axis. So if I go back to what we just did a moment ago, what is it going to be if I take I hat dot j hat?
Cosine of 90 degrees?
Cosine of 90 degrees, which is
Oh.
0.
0, right? It's 0. So both of these terms that have I hat dot j hat are just 0, right? Because these are I hat and j hat are two perpendicular vectors. If you dot product them together, it's 0, right? So I hat dot j hat 0. J hat dot I hat still perpendicular. That's also 0, right? Both of those terms go away. What about over here? I've got an I hat dot I hat. Can I simplify I hat dot I hat down? What is that? If I use this or look at one of these shortcuts, what am I going to get if I do I hat dot I?
Cosine 0 degrees, which is 1.
Which is 1, right? I hat dot I hat is just equal to 1, right? Because length 1 times length 1 times cosine of 0, which is 1, just gives us 1. Right? So I hat dot I hat, that's just 1. And same exact thing with j hat dot j hat. Right? That's also 1. So that means we get a nice simple equation now for the dot product if we know what the components are. So A dot B is just equal to the x components multiplied together, ax, bx, right? These are not vectors anymore. These are just numbers, right? Components. And then plus ay dot by. Or sorry, ay times by. Those aren't vectors anymore. They're just numbers. You just multiply them together normally. So this is another useful equation. If you need to take the dot product of two vectors and you know their components, but maybe not necessarily their magnitudes or angle, this is a quick way to find the dot product. We just multiply the x components together, multiply the y components together, and add them up. And we're going to be seeing the dot product a lot, so you're going to become very familiar with using this equation and this equation. Questions on the dot